Now.
Right, okay, so spin dynamics lecture 2. As I noted in the previous lecture, before starting to theorize about spins, we are looking in detail about data processing and acquisition. And from the Fourier transform that we have derived from essentially cogito ergo sum in the previous lecture, a few things follow. And we're exploring them today. And the purpose is to allow people to understand and perhaps to avoid the common pitfalls of data processing and data acquisition, and to an extent gain knowledge about how a spectrometer records data and how to make the best use of the data, because if a few parameters are not set correctly, then your signal to noise might be a factor of 10 below from where it should have been, or some frequencies might appear in incorrect positions. And so it is important to understand how the digital signal processing works and how signals are acquired. And in many cases it is possible to make some shapeless bump that the spectrometer returns, resolve itself into a collection of beautiful peaks by just doing your data processing. Okay, so what we'll start with is basic recording of oscillatory signals. What you would typically have is an FID at the end of your pulse sequence that would have time, that would have current in the detector coil, and it would be an oscillation. One of the very first questions that spectrometer hardware would need to ask the user before it acquires the data is how many points, how many data points to put in here to digitize this oscillation. Clearly, if we put a lot of points, the spectrometer hardware might not be able to cope with it, because the time scale of these things is usually microseconds, and if we ask for sub-nanosecond time resolution, it might be instrumentally difficult. And if we do sampling with too few points, then we run in danger of not actually correctly digitizing our signal, and so information might get lost. So a reasonable and important question in that regard is to what is the adequate, as it were, level of signal sampling that guarantees that no data is in practice lost, but does not overtax the spectrometer hardware beyond its physical limitations. An example of that sort of question and of how it might get wrong if it's not set correctly is given in your handout in figure 1. I've given a particular oscillation which was digitized with 1000 points, and you can see it's perfectly reproduced. Then with 1/5 of the number, 200 points, then 100 points, then 50 points, and you can see at 50 points it starts showing sharp points. But then suddenly at 25 points, the frequency is completely wrong, because the points fall in between the ups and downs of the original signal. And if we do the sampling with 25 points, then our frequency would be incorrect. Now what happens in the spectrometer hardware actually is the hardware always digitizes the signal at the fastest rate it can cope with, so usually about a megahertz, so a million points per second. But then it downsamples and averages the nearby points to return you the sampling rate that you asked for. That has the advantage of improving the signal-to-noise ratio as well. So the answer to this question is surprisingly simple, and it's called the Nyquist condition, from the name of the person that first formulated it. And the Nyquist condition says that in order to digitize a particular frequency without errors, you need to have 2 points per period of that frequency in your digitization. Equivalently, if you have multiple frequencies in your spectrum, then you must have the corresponding free induction decay, the corresponding oscillation, digitized at the 2 points per period of the fastest oscillation present in the signal. That is to say, if we have a spectrum that is stretching between, let's say, -10 and +20 kilohertz, then the fastest frequency that you'll see in that spectrum is about 20 kilohertz. So we should be sampling at 40,000 points per second, so at 40 kilohertz, at twice the amount, at a minimum, in order to sample that signal rate. Now, if we do that, so if we've done adequate sampling, and we've reproduced the signal correctly, then the Fourier transform, as we discussed in the previous lecture, would create a signal, and it would be at a correct position, somewhere in the spectrum. The consequences of oversampling here, so if we put a huge number of points here, so way more than is necessary, of course the signal would still be digitized correctly. But you should remember that every point carries a signal component when it is registered, but also a noise component. So every time a spectrometer wires this point, it takes a bit of data, but it also picks up a little bit of noise from the circuitry. And after the Fourier transform, it so happens that that noise actually survives, and it is here on the baseline. So the practical consequence of Fourier transforming a heavily oversampled signal is, first of all, you'll have a huge stretch of useless data on either side, because you digitize huge frequencies that you don't actually have. And second, the signal-to-noise ratio will get considerably worse. If you then tell the spectrometer to sample it at a slightly slower rate, so you can still digitize your signal, what it will do internally is it will average nearby points in a slightly more sophisticated way than I'm showing here, so that things don't get shifted around. The signal will grow proportionally to the number of these points. The noise will grow as the square root of the number of these points, the central limit theorem from statistics. And so the noise would get reduced. But clearly, if we overdo this procedure, then we'll fall afoul of the Nyquist condition, and the frequency wouldn't be digitized correctly. So the bottom line is, if you oversample your signal, the noise increases. If you undersample your signal, the frequencies get distorted. So the optimal sampling in almost all cases is precisely the Nyquist sampling. So in order to get the frequencies correct and the best possible signal-to-noise ratio, you should frame your spectrum so as to be close to the edge of the outside signals, and that would mean that you are both satisfying the Nyquist condition and taking the best possible advantage of the local averaging that the spectrometer digital signal processing gets.
Excuse me.
Yes.
The optimal uniform sampling
Optimal uniform sampling.
is sampling with Nyquist conditions.
Yes. Non-uniform sampling is currently under development. I do not think there's an actual criterion. And then you've got to reconstruct the Fourier transform in the least square sense or with maximum entropy. These are non-linear processing techniques which the community frowns upon at the moment. So yes, the best uniform sampling is the Nyquist sampling. An illustration of what can happen if you are slightly below the Nyquist threshold is in figure 2. So the bottom trace has been sampled correctly, and you can see in the gray area two signals which the chemist would know correspond to metal signals. And if our frequency range is correct, they should be on the extreme right of that spectrum, next to omega n. However, if we sample slightly slower than we should have sampled, then these frequencies disappear from the right edge of the spectrum and reappear on the left edge with incorrect frequency and oftentimes also incorrect phase. Clearly something that we would ideally want to avoid, and so please always check that your sampling rate is right. On modern spectrometers, what happens is there also is a bandpass filter at the end, so the signals that fall outside the spectral window oftentimes are not reflected, but are instead suppressed. So if you are not digitizing them properly, chances are you might lose even the reflections, and so not even be aware of the existence of the signal. So bottom line, when you are recording your free induction decay, the best constant time sampling is the Nyquist sampling. Now, this sampling in the time domain here has its counterpart in the frequency domain. That is, once you've done a Fourier transform and you've recorded the actual signal, there it is. you can, of course, have different number of points here as well. You can digitize it extremely carefully, a large number of points, or you can digitize it really crudely. And another reasonable question, just like we had in the original time domain signal, is how many points should one normally have in the frequency domain in order to reproduce all the signals right in here, and more importantly, in order to do the correct spectral quantification, because usually when we process our data, one of the crucial parameters in here is the integral of the data. And if we digitized it using those circles, you can probably tell that when we integrate this thing, the integral isn't going to be particularly accurate. The second important parameter that every line has is the position. And the maximum of the true line in this case is clearly different from the maximum of the line that we have here. So it is in our direct interest to find a way to optimally sum the frequency domain signals as well. And there's your figure 3, which gives the frequency domain equivalent. There's a signal and a slight shoulder on the side of it, which indicates the presence of something else, some kind of a mixture in your spectrum. And 1,000 points, 200 points, 100 points, 50 points sampling gets things mostly correct. Then 25 point sampling loses the shoulder, it's no longer visible. Then an 11 point sampling not only loses the shoulder, but is also likely to have an incorrect integral. So when we're doing spectral quantification, this digital resolution is becoming important. Now, thankfully, there is a very simple, straightforward way to improve this digital resolution in the Fourier domain once you have recorded your free induction decay. It really costs you nothing, and it improves this resolution, and the technique is known as the zero filling. This is something that you've probably seen on spectrometer processing menu if you've done any actual spectroscopy so far. If you haven't, don't worry, you most certainly will. This is one extended persistent version. So what zero filling does is, well, I'll first draw you a picture of what it does, and then I'll explain mathematically why it succeeds in doing what it does. Is it takes this signal and, well, it just adds it with zeros. So what we had is the original signal here, and in principle we could have recorded it for a longer period of time, but really the only thing that we would have had here is just a track of noise. All that noise would have reflected through the Fourier transform into the signal, and the signal to noise would have dropped. But since we know anyway that there is no signal in here once the free induction decay has decayed, what we can do instead is add it with zeros. Zeros have got the benefit of not having any noise, so we wouldn't incur the signal to noise penalty in this process. Now, seemingly a trivial procedure. We're not actually doing anything to the data. Here's our meaningful data, and what can possibly be the point of adding it with an extra bunch of zeros before Fourier transforming it? Well, let's take a look. So the original spectrum, as you saw in the previous lecture, was a discrete Fourier transform of the free induction decay, the result of our pulse. So the nth point of that spectrum would be the discrete Fourier transform, so that would be 1 over the normalization factor, root n over 2 pi. The Fourier integral becomes a sum from k equals 0 to n minus 1, where n is the number of points in there. Fk, that's the kth point in the free induction decay in here, times the Fourier term minus ikn ikn small divided by n, which is again the normalization factor, and k would be the frequency in there. So this, I think, yeah, that's summed over k, and then n is the frequency. Let us see what happens if we simply pad the signal with, let's say if this was n points, let's pad the signal with n zeros and see what happens to the Fourier transform. Well, it's the same fn, so the nth point of the Fourier transform will be 1 over 2n because we now have two endpoints in here, but it's just an overall multiplier, it's inconsequential, root 2 pi, but let's see what happens under the sum. The sum is over the entire time domain signal, so it will now be from k0 to 2n minus 1. And also it will have fk e minus I kn divided by 2n. But then fk's beyond n are zeros anyway, so the extra terms in this sum don't matter, so we can just drop them because they're zeros. What we get is 1 over 2n root 2 pi. The original Fourier sum, k from 0 to n minus 1, fk e minus I k n over 2n. Who can tell the difference between here and here? Frequency. The frequency step was 1 over n here, and it's 1 over 2n here. The frequency step became finite by a factor of 2. So if the original signal was like that, and was maybe digitized pretty crudely, once we zero fill the time domain, we put extra points in between. And if we zero fill it by a factor of 4, we will put extra points here. And you can see the signal definition becomes much better. Integrating this would produce much more accurate results. The maximum position would be reproduced a lot better. So a seemingly trivial procedure of padding the time domain signal with zeros improves. It of course doesn't improve the resolution and doesn't give you any additional data, but it interpolates the signal much better than it would have been interpolated otherwise. And in a better interpolated signal, you can get a better position of the maximum and a better integral. And in fact, the entire procedure of taking a signal, doing an inverse Fourier transform, so going from here to here, adding it with zeros and doing a forward Fourier transform, is known in digital signal processing as harmonic interpolation. It is extremely useful, and it takes any frequency-bounded frequency domain signal, and it improves the digital resolution of it for subsequent quantification. So when you start processing your own magnetic resonance data, make it absolutely certain, before you quantify it or integrate it, that your digital resolution here is sufficient, and the best way of doing that is this. One other thing it can be done, used for, is, for example, image smoothing. If you've got some pixelated, horrible image, which is in 2 dimensions, you can do a backwards 2D Fourier transform, do a 2-dimensional zero filling, do a forwards Fourier transform. You will see that the image has been smoothed with the minimal amount of broadening in there. That's one of the best ways of improving the resolution of a digital image. And so on and so forth. These things are fairly widespread. And even if you were given originally, it could have been a chromatography result here with a bunch of poorly digitized pics. Do backward transform, zero fill, do forwards transform, you will even improve the quantification of a chromatographic trace. It doesn't have to be NMR, it's a general digital signal processing tool. So this is what zero filling is for, and this is what it does. And it is usually not a good idea to cut the FID immediately after it decays. Typically, people would zero fill it by a factor of 2 to 4, just to make sure that the subsequent quantification is actually.
Interpolation is a linear procedure.
Well, this, because it's one Fourier transform followed by another Fourier transform, it inherits the linearity. But the interpolation here is harmonic.
Of course, interpolation is harmonic, but the filter is linear.
Filter is linear, definitely. Well, in a filter sense, it's not even a filter. I mean, if you look at it as a continuous unitary transformation, then it's a trivial transformation. It's just for a digitized signal. But it's linear in the original subspace, in that if your original signal was an endpoint vector in an n-dimensional space,
sum of two signals.
Your subsequent signal is a 2n dimensional vector in a 2n dimensional space, but if you project that vector into the original space, then you hit the same points exactly. So the points that there were stay where they were. It's just they're interpolated. Right, next thing, bandpass filters. It so happens, and the chemists have certainly seen it many, many, many times, that when you do some recording of, for example, a chemical kinetics trace, what you would do is you'd prepare some solution, you'd get a reaction going in there, which maybe produces some color change, you stick it into a spectrophotometer, which measures the color density as a function of time, and the reaction will proceed. And some product will get accumulated and then get consumed, and this is the kind of picture you get, where this is the dynamics of your concentration, it will be optical absorption as a function of time. And because the spectrometer is not perfect, and really the sample is probably quite dense, there's noise on top of it. So there's some genuine signal, and there's some in here. One thing that's immediately clear visually from here is the frequency of your useful signal is quite slow. It slowly rises and slowly falls. But the frequency of your noise is pretty high. These are random fluctuations in the number of photons that are flying into the detector, plus the random fluctuations of whatever electrical circuits you've got in there, and so on. Now, the important thing is the noise frequency and the signal frequency are well separated. So if we think about a filter that only lets the low frequencies through, we can in principle get rid of most of the noise here at no cost to the useful signal. And such a transformation is called a bandpass filter, because it allows certain frequencies to pass it, and those would be our useful frequencies, and certain frequencies it stops, and those would be the frequencies of our noise. And much of NMR data processing, as we'll see in a moment, revolves around the bandpass filter. So, if you look at figure 5, it's a slightly simpler signal. I've chosen it to be an exponential decay, so let's draw an exponential decay here with a noise on top of it. There's our noisy exponential decay. Exponential decay is a decaying oscillation of zero frequency. If we do a Fourier transform, there will be a signal at zero frequency. So ft, then it will be a bunch of noise, and then our signal, and then a bunch of noise. Well, this noise here and that noise here we are not really interested in. It carries no useful information. Why don't we multiply it by 0? So we'll multiply the thing by a function that will be 0 here, will be 1 here, and will also be 0 here. It will suppress this lobe of the noise, it will suppress this lobe of the noise, but the signal will pass. And so that will be the f forward. That's known as m, magnitude transfer function in the jargon. And let's do the f minus. And what we'll get is a decaying exponential with a much smaller amount of noise. Because all the frequencies that were different from a zero frequency, with a little bit of leeway so that we don't actually destroy useful information, have been suppressed. And it is another linear process which all of you, as we'll see in a moment, do every time you do apodization on your free induction decays. And, well, so our filtered signal, F filtered, put a squiggle on it, of time, is a backwards Fourier transform. So F minus applied on top of a forwards Fourier transform, F plus of the original function f of t, multiplied by the magnitude transfer function of omega. Let's see, Fourier transforms linear. If you put a sum of two functions, you get a sum of Fourier transforms. Multiplication operations linear. backwards Fourier transform is linear, and so the whole procedure is in fact a linear filter. And linear filters are something that in a mass spectroscopy generally deems acceptable as a digital signal processing technique. With nonlinear filters, we'll get to them in the next lecture. And well, that's the typical outcome. So if you have a noisy signal where the frequency of the noise is significantly different from the frequency of the signal, you can suppress the frequency. Where this is used in practice outside magnetic resonance is karaoke. If you've got some pop song, the frequencies of human voice occupy, in fact, a pretty narrow band. They are in the region of perhaps from about 200 hertz to about 2 kilohertz, typical voice. And even if you suppress some other frequencies but leave those in place, the voice is still recognizable. But music, of course, occupies a much wider range, and music is a lot more predictable. You can reconstruct missing overtones from other information. So what karaoke people are doing is applying a bandpass filter on the frequency of human voice. The result being that much of the music survives, but the volume of the human voice on top of it goes down by a very significant amount. And so it can then be replaced by some drunken voice of whoever it is that is singing that karaoke. Of course, the other thing that you can in principle do is not suppress or enhance. You can actually enhance as well. Yeah? You can multiply it by 2 rather than 1. You can shift. You can clip it from here and stick it in there, in which case the frequency will get shifted in the backwards Fourier transform. And so a voice can be modified. And this is how all those voice obfuscation software actually works. It does a Fourier transform, it rejigs the frequencies and does the backwards Fourier transform. The voice is still recognizable, but it sounds belongs to a different person. Because our ears are tuned to see a specific frequency, but when we are recognizing a person's voice. So this bandpass filtering, some radio astronomers, for example, will be looking for some artificial intelligence on a nearby star. And as you know, the frequency that people are generally looking at these days for artificial intelligence is 18 centimeters. Yes, the frequency of interstellar hydrogen. The problem is certain overtones from mobile phone hit somewhere nearby, and some satellites passing overhead. So if the dish were recording every frequency it could record, there's no hope. So what Arecibo telescope has in it is a pretty sophisticated chain of bandpass filters that only pass through that specific, I think it's 21 centimeter frequency, but cut off everything else. So that they only record something that genuinely comes from the sky, but isn't instead caused by somebody's mobile phone ringing. Same applies for NMR spectroscopy. You know, we all operate between about 100 megahertz and about a gigahertz, and the frequencies of modern memory chips, CPUs, mobile phones, and stuff like that actually fall into precisely that range. And so these long tubes that you've got on age-length spectrometers these days are actually bandpass filters intended to purify the incoming signal from all the unnecessary frequencies which would have otherwise caused the extra noise when they were digitized. So when you read something on the tube saying 19F bandpass filter, please use it. It's going to improve your signal to noise by a considerable amount. It's just a hardware filter. It's a little piece of electronics that acts as a bandpass filter. But the bandpass filter can be applied in this way mathematically as well. And it is done both instrumentally as a detection point and mathematically as a point when the data is being processed. Right, so much for bandpass. Now, okay, we've recorded our data. Yeah? We got it, we Fourier transformed it, we took great care to zero fill it right, and made sure we collect and connect all the necessary bandpass filters, and the signal is still noisy. What can we do about it? Well, we can start doing some local averaging on it. So I'll draw a signal now and try doing some, well, what would appear to be a pretty naive transformation. So let this be our really, really, really noisy signal. And to those who did practical NMR spectroscopy, yeah, it's not entirely unfamiliar, is it? This is what you get if you just do a Fourier transform without apodization. And what apodization means, I'll tell you in a moment. Right, so what we can in principle do here is to say, well, okay, there's a hell of a lot of noise in here. But it's different at different points, and it would seem that the signal is pretty broad. So why don't we do the following? We take this point and multiply it by 1. We take a nearby point and multiply it by something else. We'll take a Gaussian bell. Then we'll do the sum. That is basically an average with a Gaussian weight over all the nearby points. And put 1 point in the result. Then shift this bell a little bit. Take this point with high weight and nearby points with slightly lower weight. Do the averaging and put another point in the result. Of course, because we are averaging over a pretty broad interval here, the noise will get reduced. But what will also happen is the lines will get broad. So the result will be this. Something that has little noise in it, but perhaps a little bit of line. Let's look at what we've just done. We have taken a collection of points, averaged them out, and put a point in the result. How we can write that in a form of a mathematical transformation? Well, mathematically speaking, what we would have is our filtered signal, f of omega, would be an integral. Remember that the continuous version of a sum is an integral of our original signal, which would be f of nu, frequency, multiplied by this Gaussian, we'll call it t, which has been shifted from its original location to where we want it, so it's omega minus nu, and then summed over the frequency interval. Who recognizes the integral? Convolution. That's the signal, that's the Gaussian, the averaging envelope, and that's the convolution integral. Equivalently, we can say that our filtered signal, f of omega, is f of omega original, convolved. The convolution operation is defined as that integral with some bell-shaped g omega. But what we also know from the previous lecture is that convolution in the frequency domain is equivalent to multiplication in the time domain. So if we look not at the spectrum, but at the free induction decay, we would have had to multiply a few things together. So let us look at the corresponding FID. This was our really noisy FID. Yeah, so an inverse Fourier transform of this. I wouldn't draw the noise, it's just noisy, and the forward Fourier transform produces that, and the backward which transfers the FID. So let's look at the inverse Fourier transform of that pig. It's usually a Lorentzian curve. It's 1 over 1 plus omega squared. When omega equals to 0, it equals to 1. When omega is a large number, either positive or negative, it's 0. And it sort of transitions in between. So it's a peak. Yeah? Let's do an inverse Fourier transform of this peak. And what we'll immediately discover after we do the math, minus infinity to infinity, 1 over 1 plus omega squared, e I omega t d omega. I'll skip the mathematics. This is not the mathematics class. You can all take integrals, so you can just type it into Mathematica. But it's e minus t, the decaying exponential. So the Fourier image of this is the exponential. And whereas in this case we had convolution, in this case we would have simple multiplication. So who recognizes the procedure? Yeah, exponential apodization. The standard stuff that you do first when you acquire your spectrum to get rid of the tail noises. And, the students who haven't seen a spectrometer yet will see a spectrometer at some point. But this is the first standard thing that people do when they process NMR data. They multiply it by a decaying exponential to kill the tail noise here. But what the procedure really is, if you look at what it does to the spectrum, is local averaging with a Lorentzian weight. So bottom line is the window function of any type that you apply here, or apodization function, it's got many names, is equivalent to convolution filter averaging in the frequency domain. Now, if you've seen convolution filters before, you know that not all of them are broadening, there are sharpening convolution filters. And in principle, if we multiply it by a different function, the one that's not decaying but is rising instead, what that would do is, of course, generate a lot of noise because we'll be amplifying the noisy part of the FID, but it will also improve the resolution. So the practical consequence of this is by using this digital signal processing, it is possible to trade some noise for some resolution and some resolution for some noise. So if you have an extremely noisy signal, you can have a smooth signal if you sacrifice some resolution. But if you have a broad signal but with extremely high sensitivity, you can sacrifice some of that sensitivity to improve the resolution. So there goes. So the bottom line is, as it shows in figure 7 in your handout, that the Lorentzian smoothing convolution filter in your signal domain, in the frequency domain, is equivalent to the exponential multiplication in the time domain. Okay, let's take a look at this in a little bit more detail. So what our signal is two things. One is the oscillation, the sinusoid, and the other is the decay. And when we multiply a sinusoid by the decay, we get our actual free induction decay, and it usually looks like this in NMR spectroscopy. The result. Let's do the Fourier transform of these things independently. So this is e to the minus t, and as we know from that equation over there, the Fourier transform of this is Lorentz, 1 omega squared. So a bell-shaped curve at 0 frequency. The Fourier transform of a non-decaying sinusoid is slightly more sophisticated from a mathematical perspective. You can, I guess, simply trust me that this is a delta function. So f of omega will be 1 over root 2 pi, the Fourier transform minus infinity to infinity, e minus I omega 0 t. This signal at the frequency omega 0, then e minus I omega t, the Fourier transform multiplier, dt, that's root 2 pi delta function at omega minus omega 0. An infinitely sharp peak. So, but at a specific frequency, omega 0. So you see, NMR spectrum has two components. It has the component that determines the frequency, where the signal is, and that's the oscillation. And it has the component that determines the signal shape, and that is the decay. So the bottom line and the final conclusion from this is it is the frequency that determines the line position, but it is the decay envelope that determines the line shape. And one practical result of that, because the decay envelope is rather easy to manipulate, we could simply divide away this exponential and multiply in something else, like a Gaussian. It is very easy to manipulate line shapes. So if it decays like an exponential, it would be a Lorentzian curve, but if we can make it decay like a Gaussian, we know that the Fourier transform of a Gaussian is another Gaussian, so it would be a Gaussian curve instead. And what we know also is the wings of a Gaussian are much narrower, so such a transformation would improve the resolution. But it is still a linear transformation, as we've proven, and because Fourier transform is unitary, what it will also preserve is it will preserve the signal norm, so the integrals of those signals will stay the same. So no matter what sort of shape we are assigning to them, when we integrate them, that is when we quantify the spectrum to find out how much stuff we've got in there, it will still be a correct answer. And so long as it's a symmetric line shapes that we're doing, the frequency also wouldn't change, because the frequency is determined by the oscillation and not by the decay. And this is the rationale behind the considerable liberty we have in NMR spectroscopy in this data processing. Because no matter what you do to the envelope, you can never alter the frequency, and so the frequencies will also be in the correct shape, in the correct place. And no matter what you do to the envelope, you still don't change the integrals, and so the quantification will also be correct always. But the spectral resolution might improve considerably, and you would be able to resolve signals that would not otherwise have been visible. So all of that is summarized in figure 9. So your FID, free induction decay, is a product of an oscillation and a decay envelope, and the oscillation determines the line position, and the decay envelope determines the line shape. And because the decay envelope is easy to manipulate, it is also easy to manipulate the resulting line shape. And this is the next topic, which is, well, encountered surprisingly frequently. Certainly, you're only starting to do NMR spectroscopy, you'll be in a few situations like that. Namely, either forgetting to shim your magnet, or not shimming it properly, with the result that some pretty expensive sample might have a terrible line shape and also be completely spoiled by the time of the experiment has finished. And so you need to recover high resolution data from pretty low resolution stuff that came out of the spectrometer. And this is one of those advanced processing techniques that Yuri would like. If you've ever misaligned your z-squared shim, you'll see what I mean. So magnet, NMR magnet, needs to be tuned to very considerable precision. We are looking at splittings of the order of 1 Hertz in a 600 megahertz magnet. That is, the magnetic field inside has to be stable to 1 part in a billion. It's pretty difficult to achieve that stability, and there are multiple electronic systems in place to maintain that stability. But, well, there are situations where they simply don't cope, and the magnetic field across the sample would vary by several ppb, and that in practice means that the signals get distorted. What's important, though, is because it's the entire sample that's sitting in that situation, every single signal gets distorted in precisely the same way. So what we had was perhaps a signal here and a signal here and a TMS reference here. In a perfectly shimmed magnet, it would have been beautifully like that. But if a magnet has drifted during the experiment, what we'll get is something like this here, then straight maybe on top of it, something like this here, and then our TMS will also look like that. Clearly, these things now overlap, and it would not be possible to independently integrate them unless you fit them with some functions that you know what it is, but you don't know what it is. And so the task is to reconstruct from the distorted data the original beautiful spectrum. Now remember what I had said about the line shape, that it is the property of the decay envelope. And the procedure of reconstructing this thing is known in the trade as reference deconvolution. And the reason it works, and I've drawn this separate single peak here for a reason for TMS, is this peak can be used as a reference. If we translate it to zero frequency and inverse Fourier transform it, it would give us the envelope. Yeah, so it will be this incorrect envelope for the decay that we've got. Well, we take this envelope, what do I call it? I call it R of T. So we take our horrible FID that was under that envelope, and we simply divide it by this. what we recover is the original oscillation with necessarily infinitely sharp lines and therefore a huge amount of noise. So it would not be usable. But what we can do afterwards is multiply it by a nice beautiful exponential instead of this original horrible envelope that would recover Lorentz inventions. So then what we get is nice exponentially decaying oscillations and forward Fourier transform returns here. So the whole process, therefore, is to recognize that this spectrum, the experimental spectrum, is a convolution of our ideal spectrum with some instrument response function, it's called, or omega minus omega prime omega prime. Should be a prime here as well. And this is a general case of a linear filter. Here, all instrument response functions look like that. In EPR spectroscopy in particular, this often occurs and is very significant for that reason. Then, when we backward Fourier transform this, we remember that convolution in the Fourier transform representation becomes multiplication. And so what we get is the experimental FID becomes the ideal FID of time times our instrument response function. We can determine the instrument response function from the reference peak. We can divide it away from here. That gets us as ideal. And we can then multiply it by E minus lambda t, which is a nice exponential decay envelope that will get rid of the noise. And we return to our beautiful signals. So assuming you have a reference, which is of course not always the case, but people typically put a reference substance with a single particular sample, it is possible to reconstruct distorted spectra, assuming of course that the entire spectrum has been distorted in the same way. The other problem with this, of course there's no magic. The signal to noise cost of this is close. So if you had extremely high signal to noise ratio, several thousand, and you applied this kind of reconstruction, the result will be sharp and beautiful but pretty noisy. So unfortunately, as with many dramatic resolution enhancement techniques, this transformation, although well defined, tends to blow up the noise considerably in the data. So, but we had a few situations where that was the case, and we could salvage some pretty bad looking data from, as you can probably guess, this comes from a Z-squared shim misalignment situation, because if it's a Z shim, it's much easier because the distortion would have been symmetric, and a simple Lorentz-Gaussian transformation would have done the job just as well. So that is reference deconvolution, and yeah, forgive me if it looks a bit eclectic for the people that haven't sat on the actual spectrometer yet. As soon as you get to record your own data, you'll see what I mean, and it often gives great satisfaction. You know, you get some horrible blow out of that instrument, and you know, with a little bit of fiddling here and there with MATLAB, or maybe just with a mouse and standard processing suites. Mestranova is pretty good actually on this DSP side of it. You can actually make it beautifully resolved and get the noise down and do much nicer quantifications that otherwise have been possible. And understanding how this stuff works gives an even greater satisfaction, because you don't simply see that it works, you also know why it works.
Just a quick question.
Yes.
How we know lambda?
You just choose it. 1 over lambda is the resulting width of this line. You say it's a balance between the resolution and signal to noise. So it will have noise here. So you choose lambda in such a way as to have a trade-off between the width of the line and the amount of noise in the spectrum. So basically there's a line shape to put on these signals afterwards is your choice. Right. Final topic for today, SVD denoising. Another exotic data processing practice, but which comes from MRI, from magnetic resonance imaging, rather than NMR, where it is used very extensively. and it is useful in situations where you have not just a single spectrum, but an array of the spectra, where the signal is either the same or similar between the instances of the data in the array, but the noise is completely different. And of course, that's the standard situation in your data acquisition, because if you have a sample and a noise and you record multiple spectra of that sample, then the noise would be different in every instance, but the signal would be the same, and that can be exploited. Now, as I said, it's not applicable to a single spectrum, or rather, it would not yield any benefit in the case of a single spectrum. It's an identity transformation in that case, but it is useful when you've got arrays of data such as 2D spectroscopy, magnetic resonance imaging, or chemical kinetics research, where you record multiple traces under tight time constraints. So you cannot actually average indefinitely because there's chemical reaction going on in your system. Right, so the situation is that, let's say we've recorded a spectrum at a particular time point, then the same spectrum at a slightly different time point, then the same spectrum at the third time point, and something happens to the intensity. So maybe new substance appears in the sample, or it gets consumed, or it gets removed. Anyway, the intensity of this thing changes. In here, there are two parts to every spectrum. There is the part that is correlated between these spectra, so the peak. It might have different intensity, but it is in the same place. And so there's a certain amount of linear dependence because of the peak between these vectors. And there is a part that is independent, because the noise is different in every instance. The noise parts would remain uncorrelated. Singular value decomposition is the procedure that allows you to filter the parts which are similar between different instances or linearly dependent from the parts that are independent in every instance. So what would happen if you do an SVD, if you take this as a matrix of data and do tell a program to have a singular value decomposition? We'll be done in about 5 minutes. Yes.
I need to set up my computer.
Please go ahead.
I'm lecturing 5 minutes.
So that matrix would have a decomposition, U sigma V, where U and V are the signals that occur, or the noise tracks that occur, and sigma contains the corresponding statistical limits. And a singular value decomposition actually sorts these subspectra into parts with different statistical. And if you examine the vectors in here, you will either see the signals, in which case you want to keep them, or you will see just the noise track, in which case you can ignore them. So the procedure here is to inspect the corresponding components, find those which contain signals and keep them, find those that contain just noise and eliminate them, and so you'd have U, let's say, squiggle, sigma squiggle, V conjugate squiggle, where the noisy parts have been eliminated. You reconstruct the data matrix, and that is the denoised data matrix. And I've given an example, figure 10. This is from our actual research. This is a chemical kinetic space for a refolding of a protein that has been SVD denoised. And you can see between the top picture on left and right, the improvement in the signal to noise is about a factor of 10 in this case. So the bottom line is SVD eliminates linearly independent, statistically insignificant components. Dima would know that this is a Frobenius non-approximation to the original matrix, and it allows you to extract useful data and get rid of the noise in practical situations. But it needs your data to be an array. It cannot work on a single spectrum. Okay, end of the lecture. See you next week. Okay. Thanks for letting me finish. Because it's on the video, so.